last class we saw what a red-black tree was. We saw the correspondence of red-black trees and 2,4 trees. Then we saw the deletion process in red-black trees. So, this was an extensive process with 6 cases and so on. Today, we are going to see how to insert a key in a red-black tree. We are then also going to introduce the notion of an A-B tree. So, we will first define what an A-B tree is, and then we are going to see the process of insertion and deletion in an A-B tree. So, we get to insertion. So, suppose we are trying to insert a key k into a red-black tree. So, after all, a red-black tree is a binary search tree. So, it is a binary search tree. So, first the insertion process would be as is in the case of a binary search tree, which means that we would try to find whether the key already exists in the tree. If it exists, then we would not insert it, right. If it does not, then we are able to identify the place where the key has to be inserted. We create a node with that key, we put it at that location, and now we have to color this node, right, because after all a red-black tree differs from a binary search tree in the fact that each node is colored and this coloring obeys certain properties. So, now we color this node and we are going to begin by coloring this node red. Okay. So, let us say this is the node that I inserted, yeah, this has key k in it. So, which means that I must have come in my binary search tree, I must have come up to this node, gone right because k was larger than this key, and found that this was an external node, right. Earlier in the binary search tree this was an external node. Now, so I decide to put my node here and I color it red, and I will create 2 external nodes which will be the children of this node. Now, if the parent of this node is black, then we have no problem, right. Because this node is colored red, the black height of the tree has not changed. The black height of these external nodes is the same as the black height of the external node which was sitting earlier at this location, and which was the same as the black height of the other external nodes in this tree, which means that the black height of these 2 external nodes now is the same as the black height of all the other external nodes. So, that property of the red-black tree continues to hold. That is primarily because we have introduced a red node and not a black node. Yeah. So, the property that the black depth or the black height of all the external nodes should be the same continues to hold. The problem could, however, be one of what is called a double red, right, and that happens if the parent of this node is red, as is in the picture here, right. So, this is the node I created. If its parent is red, then we have a double red problem, and we have to handle this problem now, right. So, remember that in the case of deletion, the problem was arising because the black height was changing, and we were in, all along we were trying to take care of that problem. We never encountered a double red problem in the case of deletion. In the case of insertion, however, we will never have the problem of black heights not being uniform. The black heights of all the external nodes will be the same, no problem on that front, but the problem will be one of a double red. Okay. So, we have a double red problem, and let us see how to take care of this problem now. So, this is the node that I am inserting. So, just concentrate on this picture for now. This is the node I am inserting, this is k, right. In the previous picture I had shown that its 2 children were external nodes. Now, I am just replaced that by subtrees, and you will see what the reason for this is in a short while. And now, we would have a problem, a double red problem, if the parent of this node that we inserted is red. So, this parent, which is node A, is colored red. Okay. Now, clearly the parent of this must be a black. If the parent of this node was a red, then there was already a double red problem in my tree. So, this must be a black, and the first case I am considering is when its other child is black, which means that the sibling. So, this is the node that I am inserting, its parent sibling is black. That is the case I am considering. Its parent sibling is black. Yeah. And what do we do in this case? We just do a simple rotation, right. Note that A is larger than B and A is smaller than K. So, I can put A in the middle, B on the left and K on the right, and I get this kind of a tree now. Yeah, A will be colored black, B and K would be colored red. What is the black height of this tree now? The black height of this tree is the same as the black height of this. If you had took any external node here, its black height was whatever was the black height of this plus a 1, and for those guys it is still the same, whatever is the black height of these pieces plus a 1. Note that the black height of all of these, no, would the black height of all of these be the same? Suppose the black height of this is h, then the black height of this should also be h, this should be h plus 1, this should be h plus 1 and this should be h plus 1. So, I can actually, let us just to make sure that you understand what is happening here, let us just put down these black heights. Suppose it is h, then this be h plus 1, h plus 1 and h plus 1. And so, when I am writing down, this should be h, this should be h, this should be h plus 1, h plus 1 and h plus 1, right. And now, you can see that the black height of all the black depth of all the external nodes. So, anything here it will be h plus 1 plus 1, h plus 2, h plus 1 plus 1, h plus 2, this h plus 1 plus 1, h plus 2. So, the black height problem is, the black height problem is not there at all, it is uniform. Now, the only thing we have to worry about is whether by this transformation we have introduced a new double red problem, and we have not. We would have introduced a new double red problem if either this was red or this was red or this was red, that is the root of any one of these 3 subtrees was red. But if the root of any one of these 3 subtrees was red, then that means that we had a double red problem, we had 2 double red problems and not 1 double red problem. Yeah, we had, if this was red, then this is also red, this is also a double red problem. If this is red, this is red, this is also double red. So, we had more than 1 double red problem, right. But we have introduced only 1 double red problem by inserting that node. Yeah, so this cannot happen.
So, in this case you are inserting K.
In this case we are inserting K.
So, sir, how are you getting the 2 subtrees behind it?
Right. So, for now just assume that these are external nodes, okay, and I'll in the next slide I will come to why I have drawn these 2 subtrees here, right. You will see that shortly. Okay. Now, what does this correspond to if if I were to think of this as a 2-4 tree? If I were to think of this as a 2-4 tree, then that means that I have a node which has these 3 keys in it, right. It had earlier B and A in it, keys B and A. This was another node. Yeah, this had B and A in it, and then I am bringing in K, and so K can be accommodated here without any problem. Yeah, this is what we said, but we are getting a double red problem. Why is that? Well, it is because this is not formed in the right manner. If I had 3 keys in a 2-4 node, then the middle key is the one which is to be set blank, right, while it is not getting done here. So, just that simple rotation takes care of this. So, it is not that we are changing the 2-4 tree in any manner, right. This is the node corresponding, this is the node corresponding to the 2-4 tree. These 3 nodes go together into one 2-4 tree. These 3 nodes still go together in the same node of the 2-4 tree. Yeah, it is the same as before. It is just that we are reorganizing it so that it is now in the form of our red black tree. Okay. So, that was one case when the parent of this guy, the inserted node, has a sibling which is black. So, the other case is when this is red, right, and we will look at that now. So, this is the second case. The parent of the inserted node A is red and the other child of B is also red. Okay, and we have this double red problem and we need to take care of this. Okay. What should I do now? Can I do what I did on the previous slide? Why not? Because then I would get a double red problem on the other side, right?
Corresponding to 4 tree, they are having complete
Right. So, what is happening? Good. So, what he is suggesting is that in the, if I look at what is happening in the 2-4 tree, so that means that in the 2-4 tree, this is the corresponding node of the 2-4 tree. Recall, how do I get a node of the 2-4 tree? I take a black node and look at all its red children. So, this is the corresponding node. So, it already has C, B and A in it, and I am trying to bring in K into this. Clearly, there is no space. So, what do we do? Split it into 2, right. So, that is exactly what we are going to see here. This is what the transformation we are going to do. No transformation really, but we just recolored the nodes, and this corresponds to a split, and let us see why. Right. So, this is the transformation I have done. I have colored this black, colored this black, right. So, this, the picture was C, B, A are sitting in one node and K is trying to come in, and how do we split? We split with C, B on one side, A, K on the other side, and then B goes up, right. So, B goes up, C on one side, A, K on the other side. Since C is on one side, that corresponds to a single black node. A, K on the other side, that corresponds to A and K, and this goes up. So, this is now trying to go up to the parent. Okay. Does this take care of all problems? Okay. So, there are two things, issues. First, does it take care of, so have we created a black height problem? No, right. So, let us say what should the black heights, initial black heights of all these subtrees be? Let us say they would, oops. So, if they were all, if this was H, then they would all be H, and the black height of this entire subtree would be H plus 1, right. So, which means these are all H, and now the black height of this entire subtree is H plus 1. So, no problem, it is as it was before. But now I have a red here, and its parent could have been a red. So, I have a double red problem now, right. So, it is the same thing, but now what we have managed to do? We have managed to move the double red problem up, one level up, right. And now you see why I had these subtrees hanging out of here. When this moves one level up, this will be one subtree hanging from here, and this would be the other subtree hanging from here, right. Right. So, this is the this is the continuation. So, the parent of B could also be red. In that case, the double red problem moves up one level, right. So, we will repeat this process at the next level. So, we will consider the two cases, right. If we can by rotation take care of it, we would take care of it. If not, then the double red problem will move even one level up, and so on and on, right. So, eventually what will happen? We will end up coloring the root, which was originally black, remember, in a red black tree, we will end up coloring it red. But if the root is colored red now, everything else is okay, right. It is just that the root is colored red. So, how do I take care of that? Color it black, right, just color it black again. So, what will that do? That will increase the black depth of all the external nodes by 1, but it remains the same. We are not saying that the black depth of all the external nodes should remain the same, we are just saying it should remain uniform. The black depth of one external node and the other external node should be the same, and if I color the root black, it just, it will affect all the external nodes by 1. So, there will be no problem, right. So, this essentially corresponds to moving all the way up and splitting the root. When we split the root in the case of a 2-4 tree, even then the height of the 2-4 tree went up by 1, right. And so, we are seeing that the height of the red black tree is correspondingly increasing by 1 when we do such a thing. Is this clear to everyone? Right. So, again what we have seen in this insertion process is that either we had to do one rotation to take care of the problem, and if we could not take care of the problem by one rotation, then we had moved the problem up to the next level. But when we moved the problem up to the next level, we just did a recoloring of the nodes. Yeah. Let us see, when we moved the problem up to the next level in this case, all I did was change these reds to black and change this black to a red, right. And now it is moved up to a next higher level, and maybe if it has to move up to a further higher level, it will just do correspond to recoloring of nodes. Yeah.
When we color B red,
yeah.
and if its parent is also red,
right,
then the other child must be black.
Then the other child must be black.
Because every child
right.
of a red is black.
Right.
So we finish in either one step or two steps. Because it gets to case 1 then.
Is that true? Okay.
Only
Let's see. He has a very interesting question here. Let me just check. So what he's saying is, let's confirm this. So he's saying, suppose the parent of this was red, right? Then you're saying the other child of this guy has to be black. It cannot be red, clearly, otherwise there was already a double red problem, right? So now we have a, no, but it's not this that we are worried about. It's basically this guy we are worried about, whether this is red or this is black.
So how do we ensure this process stops actually?
So where will it end up eventually? To the root. Right? So it's not this guy we are worried about, please remember. Right? If you look at the previous case, yeah, we looked at the parent node's sibling, whether it is red or black. And so it is this node whose color we are worried about, and this node can still be red or black. Okay. Right. So in the insertion, what is happening is we just have to do one rotation, right? And if we move up the tree, we just have to do recolorings. The same was happening in the case of deletion also, and I had mentioned this very clearly, right? That if we move up, we just are doing some recolorings. It's one rotation. The moment you do a rotation, the process ends. Otherwise, it's just a recoloring, right? And this is what it takes. It makes the process very fast, because recoloring is just one bit of information really in each node. You just need one bit, 1 or 0 will just tell you whether it's red or black. So you just need to quickly change those bits if you are moving up the tree. And then the moment you do a rotation is slightly more expensive because it requires some pointer changes, right? 6, 7 pointers have to be changed. Yeah. And this is why this red black tree is faster, insertion and deletion in red black trees is faster than in the case of AVL trees. In AVL trees, recall that we had to do more than one rotation. We did a rotation, then we moved up, then perhaps we had to do another rotation and so on and on. Right. So although the time is in for both of these data structures, the worst case time for insertion and deletion is log n, because even there you were doing only log n rotations, right? But the constants behind that log n are much larger in the case of AVL tree than in the case of a red black tree, right? So even within this log n, this would be a faster process, both insertion and deletion, than in the case of an AVL tree. Is everyone with me? Okay. So that's all we wanted to we are going to discuss about red black trees. So we looked at search, insert, delete. All of them take log n time, right? You know, you can also think of other operations, like if I say find the minimum element in a red black tree. How much time do you think it's going to take? Right? Minimum means just keep going left. So time is height is log n. So it's just log n. right, maximum element, all of those you can do it in log n time, successor, you can do all such kind of operations in log n time, right. Most of those operations are not changing the tree, so it is much easier. The two operations which change the tree are insert and delete, but we have seen that you can still take care of them in log n time. So, we will now come to this notion of A-B trees, and this is a generalization of our idea of 2-4 trees, right. So, what is an A-B tree? So, I have drawn an A-B tree here, and actually this is the same picture that I used for a 2-4 tree, if you remember. So, an A-B tree first of all is a multi-way search tree. Each node now has at least A and at most B children, right. So, when A is 2 and B is 4, then you get your 2-4 tree, at least A and at most B children. So, if it has at least A children and at most B children, then how many keys are there inside? How many keys are there inside? A minus 1 to B minus 1. What do you mean B minus A plus 1? If it has A children, right, if it has A children, then it has A minus 1 keys. If it has B children, it has B minus 1 keys. So, the number of keys is between A minus 1 and B minus 1, right. Did I ask something else? Now, one node which does not satisfy this property is the root node. The root node can have only 2 children, right. So, if A is 3 or 7 or some such thing, then it is not that the root also has to have at least 3 children or 7 children. Root is out of this definition. So, root can have only 2 children. So, root has at least 2 and at most B children. So, for root the requirement is from 2 to B, okay, and we will see what is the need for this. Again, all leaf nodes are at the same level, and the height. So, what is the height of a AB tree now, right. So, we have seen this before, log n to the base B is the minimum height and log n to the base A is the maximum height. Minimum would be actually you can contest this a little bit, because the root has only 2 children, right. So, the maximum height would be when the root has 2 children and everyone else has A children. So, there would be a plus 1 here perhaps or some such thing, right, but this would be roughly the bounds, okay. And this is an example of a 2-3 tree even. As you can see, every node has at least 2 and at most 3 children, yeah. So, this is an example of a 2-3 tree. So, we can talk of 2-3 trees, we can talk of 2-4 trees, we can talk of 2-5 trees and so on and on for any choice of A and B. I will correct this statement as this discussion proceeds, not any choice of A and B. We will see what are our requirements on the relation between A and B, right. This will not work for any choice of A and B, but for now we will just assume it is any choice of A and B. Insertion. So, as you can imagine, this is going to be essentially a repetition of what we did for the 2-4 trees, and it is, right, with small modifications, right. So, now I am I am trying to insert, let us say, this key 21. So, what do? It is a multi-way search tree. So, I will find the position where this has to go. So, 21 between 13 and 22, come down more than 18, go right, and it can fit into that node. So, nothing to be done. So, no problem if the node has empty space, right. Similarly, 23, come here, go right, less than 25. So, it comes to this space, and in a node we are just keeping ordered. So, let us say 23, 24 will make way and 23 will come at that place, right. You must have seen these slides before. So, why are you smiling today? Yeah, because you are seeing it for the first time. Okay, good. Now, if there is no space in the node that we are trying to put the key in, then the node gets split, right. So, let us see 29 compared with 22, more than 22 goes right, more than 25 goes right again, and now it is here. Okay, by the way, I should have mentioned that I am looking at a 2-3 tree, this picture. So, we are talking of A B, but I did not want to make A and B very large because it would not fit on a slide. So, I am just looking at A equals 2 and B equals 3. Okay? And the concepts are the same.
And the properties that all height should be same.
Yeah, that remains, right?
So that is central for all areas.
Yeah, that is the same. So, for an AB tree, the leaves all have to be at the same height, as is in the case of 2-4 tree, right. So, this is essentially a 2-3 tree. So, now this tries, so basically 2-3 trees means each node has between 2 and 3 children, which means that each node can have 1 key or 2 keys only, which is why each of those has been made with space for 2 keys. So, each could have 1 key or 2 key. Yes? Okay. So, now this can have only 2 keys, but now I am coming with another one, third. So, what do I do? So, if there is insufficient space, then split the node. I am going to split this node, and the median key is promoted to the parent. So, which is the median of these 3? 28. So, it will get promoted to the parent. So, I split, 26 goes down, 29 goes down, and 28 goes up. Yeah, this disappears and these become the children of this, right. And what else remains? This split can cascade, and we will see an example of that. So, now when I am trying to insert 7, so I will compare 7 with the first key, 7 less than 13. So, I go left, 7 lies between 3 and 8. So, I go take the middle path, come down, 7 tries to come to this node, except this node does not have enough space. So, this node gets split into 2, 4 will go down, 7 will go here, median is 5, so it will go up. Okay. And well, there is nothing left here, so we will just remove this node, we will remove it shortly. Now, this is trying to go into this node, right, except there is no space here either, right. So, once again this gets split into 2, 3 goes here, 8 goes here, and the median 5 gets promoted to the parent. Same as in the red black tree, we have not done anything which is different from red black tree, but what I am pointing out through this is that the red black tree, we need not have a 2-4 tree, we could also have a 2-3 tree, right. In the red black tree, every node had space for 3 keys. Even if every node had space for 2 keys, we can still make it work, right. And so, that is what happens, 3 goes there, 8 there, and 5 goes to the top. Once again 5 is trying to enter here, but there is no space for 5. So, first let us just reorganize this. So, these 4 children have to be the children of these 2 nodes. So, the 2 left will go here, 2 right will go here, and now let us take care of this now. 5 trying to go there, not able to go. So, this gets split into 2, and 1 key gets promoted to the parent, except there is no parent since this is the root. So, we create a new root, right, and we would go like that. Okay. And now, these are the 4 children, they would have to become children of these 2 nodes. So, the 2 leftmost will go to this, and the 2 rightmost will go to this, and this new root will have these 2 children. Okay. Now, exactly the same thing would happen for any AB tree. Do you understand what I mean by that statement? What? So, I am trying to insert, if there is space, put it there, if there is no space, split and move the median up. The median might not be unique, like in the case of a 2-4 tree, there were 4 keys there. So, the median could be the second element or the third element. आप अपने हिसाब से pick कर लीजिए, second लेना है या third. Yeah.
An AB tree has to have at least A children.
At least A children, yes.
So we can't insert into an empty node.
We can't insert into an empty node. What does that statement mean? There would be no empty node, right?
You can't have an empty node. Only
empty node
So
will be when you
at least A children, at most B children means every node has at least A minus 1 keys and at most B minus 1 keys. So this is a property. So we can also rephrase it in this way. Every node has at least A minus 1 keys and at most B minus 1 keys. Okay. Now if your tree had less than A minus 1 keys in it, right, so then all of them would basically sit in the root. So this property is not true for the root. Root can have as small as 1 key only, right, because it can have as small as 2 children. So the root can have only 1 key. More questions? Is there something not clear?
Can you repeat this part, please?
So we are saying every node has at least A children and at most B children, which means that every node has at least A minus 1 keys and at most B minus 1 keys. This property of at least A children and at most B children does not apply to the root node. So the root node has at least 2 and at most B. So the root node has at least 1 key and at most B minus 1 keys. Right? And now you can see why we said that this property does not apply to the root. Because when we went in this manner and inserted and we ended up splitting the root node into 2 and we created a new root node, then this new root node has only 2 children. Right? So we have to permit the root to have only 2 children. This is why this requirement that the root can have as small as 2 children. If we insist that the root have to have at least A children, then we might not be able to do this at all. सबके समझ में आ रहा है? नहीं समझ में आ रहा है तो पूछ लीजिए. ठीक है, हर एक नोड में एटलीस्ट ए एट मोस्ट बी चिल्ड्रन होने चाहिए. रूट के लिए स्पेशल वो है, रूट के पास कम भी चिल्ड्रन हो सकते हैं. Okay, so let's continue. So a node is split. So now we are going back to, from 2, 3 trees we are going back to AB trees. So in an AB tree we said we are trying to insert in a node. If it has space, well and good, nothing to be done, we put it there, right. How much space does an AB tree node have? Space for B minus 1 keys, right. If it has space, we will put it. If it does not have space, what does that mean? There were already B minus 1 keys there and I am trying to insert one more key, Bth key, right. Then we will split it into 2. Yes, we will split it into 2. One of the keys will go up and the remaining B minus 1 keys will get some, half will go on one side and half will go on the other side. So that is exactly what is being said here. A node is split when it has exactly B keys. You understand why exactly B? Because earlier it had B minus 1, I was trying to put in one more there. So then it means it has exactly B. One guy goes up, one of these is promoted to the parent and the remaining are split into 2. So what is the remaining? B minus 1. B minus 1 is getting split into 2. So one part gets B minus 1 by 2 rounded up and the other part gets B minus 1 by 2 rounded down. Yes, B minus 1 by 2, if it is an integer, then both of these are the same. But if it is not an integer, then एक तरफ एक ज़्यादा जाएगा, like in the case of a 2, 4 tree. 4 was, B is 4 in a case of a 2, 4 tree. So you had 4 minus 1 by 2, 1.5, but which means one side was getting 2 keys and the other side was getting 1 key. 1.5 rounded up is 2 and 1.5 rounded down is 1. One was getting 2, the other one. So one node gets this many keys and the other gets so many keys. But after the split, these two nodes are valid nodes of the tree. So it must be that our requirement that the minimum, so one node is getting only so many keys. Right, this should be a less than, sorry.
This should be at least.
Okay, this, so one node is getting only so many keys, right, which means that A minus 1, this quantity should be less than or equal to B minus 1 by 2. Thank you, this is an error. I will correct this, this should say less than or equal to b minus 1 by 2. Right? Good. You understand why this is coming? Because I am creating a node with b minus 1 by 2 keys, right? So, which means, and I have a requirement that every node have at least a minus 1 keys in it. So, this quantity should be greater than or equal to a minus 1, because otherwise if this was less than a minus 1, then there would be a problem, because this node that I am creating is not a valid node at all. Great. Okay. So, now let us look at deletion, right. So, deletion again is the same as in the case of a 2, 4, 3. So, the simple case is when I am deleting a certain node and there are more than one node in that, right. So, for instance, if I were deleting 12, there is nothing to be done, just delete 12 and it is all okay, right, because there is still one key left. But suppose I was deleting 20, then the problem would be that when I remove 20, this node becomes empty. A node has to have at least one key and at most 2 keys. So, it has to have at least one. So, what do I try to do? If a node becomes empty, then I first try to borrow a key from its sibling. The sibling of this is this, I will try to borrow one from here. And recall what was the way we borrowed? One key went up and the other, and this one came down, right. So, that is exactly what we are going to do. 20 disappears, and so 15 goes up and 18 comes down, right. And now this is a valid 2, 3 tree, right. Great. Now, what happens if the sibling has only one key? Just one second. Right. If the sibling, so for instance, now suppose I was trying to delete 23. So, now when I try to delete 23, 23 goes away. I try to borrow one key from its sibling, right. This is the only sibling I can borrow from. I cannot borrow from here, and you remember the reason for this. I am trying to borrow it from here, but this has only one key. So, if I borrow from here, this becomes empty. So, in this case, what did we say we would do? In the case of a 2, 4, 3, we merge. First try to borrow, if not possible, then merge. So, we will merge this and this. So, we will create a new node, and this will get this key, and one key will come down from the parent. So, 24 will come down, 26 will come from here, right, and this becomes my merged node, and there is only one key left here. So, it goes to the left, and these become the 2 children of this node now. Yeah, and we also saw, and this the same thing continues here, we also saw that this process could go up and up, right, because what we have effectively done is we have removed one key from this node now. But if this node had only one key, then it would have become empty, right. अगर यहाँ पे ये 28 नहीं होता तो क्या होता? If this 28 was not there, this would have become empty. So, then we would have tried to borrow one from here, but we cannot borrow one from here because there is only one. So, this would have merged, which means this would have come down, we would have created one node with 18, 22, which essentially means I would have deleted something from here. But if I am deleting something from here, this becomes empty. So, again it will merge, and this in this manner eventually it might be that the root has to be removed and the height of the tree reduces by 1. We had seen this example for the case of a 2, 4 tree. Same thing happening here, exactly the same thing, right. Okay. So, let us continue. So, in an AB tree, we will merge a node with its sibling. When will we merge a node? Now, we are coming back to an AB tree. When I merge a node with its sibling, when do I merge a node with its sibling? That is the question, right? Right. So, this node that I am merging, I have to merge with this. So, the minimum number of keys in a node is a minus 1. So, which means it had a minus 2 keys. So, I am trying to borrow one from its sibling, but I am merging with the sibling, which means that even the sibling does not have anything to lend me, which means how much does the sibling have? The minimum number, a minus 1. So, if I am merging a node with the sibling, then that means that the sibling has a minus 1 keys and the node itself has a minus 2 keys. Yes. So, after merging, the new node that gets created, how many keys will it have? The sum of these two plus 1. Why plus 1? एक ऊपर से नीचे आया. So, it will have 2a minus 1 keys. Yeah. Now, 2 times a minus 1 better be less than b minus 1. Yes. So, this is the same as saying that a minus 1 better be less than b minus 1 by 2. Why have I said floor? Well, a minus 1 has to be an integer, right? So, if a minus 1 is, so this one is saying a minus 1 is less than or equal to b minus 1 by 2. And you know, since a minus 1 is an integer, it has to be less than or equal to the floor of this b minus 1 by 2. Floor means rounded down. This symbol means if this is not an integer, round it down to the nearest integer. Okay. Did we see this expression before? Right? This was the error, right? So, this was a minus 1 less than or equal to b minus 1 by 2. If this statement was an error, a minus 1 should be less than or equal to b minus 1 by 2, right. So, what are we seeing? We are seeing that we are getting the same expression from both. Right. So, this is the property that your a and b should satisfy, that a minus 1 should be less than or equal to b minus 1 by 2, right. Okay. So, what is this? Let us just quickly see what this means. So, what are the values of that? So, given a particular value of a, what are the different values that b can take? Right. So, this you just have to look at this again, right. So, b can take a value 2a minus 1 or more. So, b should be greater than or equal to 2a minus 1. Both of them are telling us this. So, when a was 2, what are the values b can take? 3, 4 and so on, right. Is that okay? So, that is the thing that we need to keep in mind, right. So, if we have a as 5, then b has to be at least 9, and so you cannot have a 5 7 tree, this will not work, but a 5 9 tree is okay. Will stop today's discussion about or let me just correct myself, right. So, as a quick summary, what I can say is that for insertion and deletion, we saw insertion and deletion in AB trees, right, and the height of an AB tree we saw is log n, and so insertion and deletion both take order log n time. The reason for that is the same as was in the case of a 2-4 tree, right. The reason why insertion and deletion was taking log n time in a 2-4 tree was the height was log n, and we might have done some number of operations, but we were doing operations proportional to the height, right. We might move up all the way. So, first we moved down in the case of insertion and deletion. So, that is height order log n, and then some borrowing in the case of insertion. Sometimes we are splitting, but the number of times we would have to split is at most the height. In the case of deletion, we would either borrow a key or we would merge, but again the number of times we would have to do this is proportional to the height, because every time we did one of these operations we moved one level up, or we just stopped the entire process, right. So, both of these operations take order log n time, and the other thing we saw was what should be the relation between A and B for this to work, right. So, that is as far as AB trees was concerned. For the other thing we did today was the red black trees, and for that we saw the process of insertion, and we saw that it takes only some number of recolorings and one rotation to complete an insertion. So, that is the key thing about red black trees, that they only require one rotation, some number of recolorings, right. You might have to recolor many modes, but only one rotation is required, and this is what gives them their power. This is what makes them very fast in practice, right, and they are faster than AVL trees for this reason. Okay. So, in the next class we are going to see a particular kind of an AB tree which is called a B tree, and what role does it play, especially in searching very large databases. Okay. So, that we are going to do that in the next class. Thank you.